So this is a functional analysis. So functional analysis, the first topic is normed and Banach spaces. Functional analysis, basically it is a combination of algebra, linear algebra and real analysis. So we must aware of the definition of vector space and all other definitions of linear algebra, as well as the definition of the basic topology, metric space, sequence, and all the things, all the definitions related to basic topology. Now here we are going to start the first definition, which is called a normed linear space. So we are going to directly from the normed linear space. So this is a normed linear space, our first topic, and it is our first topic, and in the first topic let n be a, so this is a vector space over a field f, right? And it may be R, it may be C. If field is R, then this vector space is called real valued vector space. If field is complex, then this is called complex valued vector space, right? So that is the difference between real valued vector space and complex valued vector space. So in the real valued vector space, field is real, and in the complex valued vector space, field is complex. Now we know the definition, we know the property of vector space. So I revise it again. Property number 1, V plus should be a abelian group. It means it is a V is a additive abelian group. Property number 2, alpha x plus y, which is equal to alpha x plus alpha y. Property number 3, alpha plus beta into x, which is equal to alpha x plus beta x. And next is alpha beta x is equal to alpha into beta x, right? Next is 1 into x is equal to x. So all these are property of vector space. This is 1, this is second, this is third, this is fourth, and this is 5. So all these are the 5 property of vector space. Now these x and y, this belong to the vector space, and alpha and beta, these are scalar, so it belongs to the field. So remember this. So vector space has all these 5 properties. Now after vector space, our next definition is a normed linear space. So before going to the normed linear space, we define a sum function. This is of this kind. So remember this. So it is not of F type, G type, it is of this type. A function from n to R. What is n? N is a vector space. What is R? R is a set of real number. This is said to be norm if it satisfy the following property. If it satisfy the following property. property number 1. Functional value of any vector should be positive. This is functional value of any vector belongs to n. Property number 2. If its functional value is 0, then it implies vector is 0. If vector is 0, then it implies its functional value is 0. Property number 3, which is a triangle inequality. So this is functional value of x plus y is less than equal to functional value of x plus functional value of y. This is a property number 3. Now property number 4. Property number 4 is norm of, this is a property number 4, which is norm of alpha x, which is absolute value of alpha into functional value of x. So it is a functional value of alpha x which is equal to absolute value of alpha into functional value of x, where alpha is some scalar. Now if a function, this function satisfy all the four properties, then this function is called a norm. So this function is called a norm. Now this norm with this space, this vector space, which is called a normed linear space. This is called a normed linear space. Clear? So what is norm? Norm is a some function on n. So what is n? N is a normed linear space. So what is the property of normed linear space? Number 1, it is a vector space. Number 2, a function defined on n satisfy these four properties, 1, 2, 3, 4. Clear? If it satisfy all these properties, then it means in the normed linear space these four properties are satisfied. So remember this, number 1. Number 2, if this is some n normed linear space and this is second r, or this is a function norm, if this is some x vector, then norm of x belongs to this r. It means this is a real number. So remember that the functional value is a real number. So remember some properties to understand this property. So this is a real number. Clear? And x is vector belongs to n, and this is a real number. Now it implies x minus y also belongs to n. So it means it is a vector of n. If it is a vector of n and n is a norm space, by property number 1 it is always positive. So what is this? It is a distance between x and y. So it satisfies property number 1. It is always positive. It means distance between x and y is greater than equal to 0. Property number 2. Let distance between x, y equal to 0. So it implies norm of x minus y equal to 0. So by property of norm, x minus y equal to 0, it implies x equal to y. So it is our first part. Now reverse this process. If x equal to y, then it implies x minus y equal to 0. It implies its norm is 0, and it implies distance between x and y is equal to 0. So this is a property number 2. Now property number 3, which is a triangle inequality. Now let we take 3 vector x, y, z belongs to n. So distance between x, y, which is equal to norm x minus y, right? So this is a distance. So we can write this norm of x minus y as x minus z plus z, right? So we add z and minus subtract z, so there will be no change in this term. So this is this first term, this is second term, and these vector belongs to n, and n is a norm-linear space, and norm-linear space satisfy triangle inequality. So it is a less than equal to x minus z plus z minus y. So what is this? This is a distance between x and z. So what is this? It is a distance between z and y. So it implies distance between x, y less than equal to distance between x, z plus distance between z, y. So it proved the property number 3, which is a. Now property number 4, which is a symmetry property. So this is a distance between x, y, which is equal to norm of x minus y. So this can be written as minus 1 into y minus x, these values, and this can be written as absolute value of minus 1 into norm of y minus x, and this can be written as norm of y minus x, and this can be written as distance between y-x. So it implies distance between x, y and distance between y-x are equal. So it implies, it proves the symmetry property. So it proves all the property of metric space. If it proves all the property of metric space, then this D is metric on n. This D is metric on n, and this n is also a metric space. So what we conclude? We conclude that every norm-linear space, every normed linear space is a metric space. Every norm-linear space is a metric space. Or we can say that norm space implies metric space. Clear? So every norm space is a metric space, and its distance function is this. It is a distance between two vector x and y. So this is a distance function in this value. Now, if this norm space is complete, then it is called a Banach space. So what is Banach space? So a complete normed linear space is called a Banach space. This is called a Banach space. Clear? So this is a complete norm space which is called a Banach space. What you mean by complete? Complete space is in which every Cauchy sequence is convergent. So what is complete metric space? In which every Cauchy sequence is convergent. Now this space is also called B space, which is also called a B space. B space means Banach space. Now what we conclude, we take some n which is a vector space. It may be real or complex. Now here we define some function on n which is called norm, satisfies some property. Then this n is converted into normed space. This n is normed space. In addition to this property, this vector space will be converted to norm space. If we add another property, completeness, then this norm space is converted to Banach space. So this is a Banach space. So a complete norm linear space is called a Banach space, and if this function defined on vector space satisfy for property of norm, then it is called norm, and this space is called norm linear space. Now next is very important result. So we can also say that theorem. Now let n be a normed linear space. So in this chapter we always take n as a normed linear space. This is a normed linear space. If x and y two vector belongs to n, then it satisfy this property minus norm of y, and this is less than equal to norm of x minus y. So it is for every xy belongs to n, right? So our purpose is to prove this inequality. How we will prove this inequality? Now in this inequality, the absolute value of this is less than equal to this. It means its positive value is also less than this number, and its negative value is also less than this numbers. Clear? Now first I take this norm x. This can be written as x minus y plus y, no problem. And by triangle inequality normed, this can be written as norm of x minus y plus norm of y. This implies norm of x minus norm of y. This is always less than equal to norm of x minus y, so which is equation number 1. Clear? So this norm of y is taken on the left hand side. Now To prove second part, we just replace x and y. So just replace, interchange, replace x and y. The interchange, we can say that interchange. So interchange x and y. If we interchange x and y, clear? So equation number 1, in that case, equation number 1 becomes norm of y minus norm of x less than equal to norm of y minus x. This can also be written as this norm minus 1 x minus y, and this can also be written as absolute value of minus 1 into norm of x minus y. This can also be written as norm of x minus y. So it is a right hand side of this equation. Now what is the left hand side of this equation? This is minus norm of x minus norm of y, which is equal to norm of x minus y. So which is equation number 2. So this is equation number 1 and this is equation number 2. Clear? Now from equation number 1, its positive value. From equation number 2, its negative value. From both the equations, from 1 and 2, we get, from 1 and 2, we get absolute value of norm minus x minus norm of y less than equal to norm of x minus y. So this proved the result, right? So it is our first result to prove. This is very important. Also remember that result. Now next theorem is, again, let N be a normed linear space. So in this chapter, N is a normed linear space, right? If N is a normed linear space with the norm, so this is a norm, right? Now define a mapping F from N to R, and this mapping is defined by f of x, which is a norm of x for every x belongs to N. Then prove that this mapping F is a continuous mapping. This mapping is a continuous mapping. So remember that every norm function is continuous. So this result shows that every norm is a continuous function. So that is the another statement of this is the every norm is a continuous function. So what is norm? Norm is a function and it is a continuous function. How we can prove this is a continuous function? So basic result of to prove it is a continuous function, if we take some sequence, let xn is some sequence in n such that this xn approaches to x, and after that if we prove our claim, its image mean fxn converge to f of x as n approaches to infinity, then this function is continuous. If this sequence converge to x as n approaches to infinity and its image is again approaches to its image, then this function is a continuous. So that is the way to prove the continuity of any function. Now, our purpose is to prove this result. Since xn approaches to x, it implies norm of xn minus x approaches to 0 as n approaches to infinity. Equation number 1. Clear? So that is a given part. Our purpose is to prove that norm of fxn minus fx approaches to 0. So this is fxn minus fx, right? Clear? Here I take the absolute value because norm of real number is absolute value. By substituting the definition of function, which is a absolute value, norm of xn minus norm of x. So this values. By previous result, this is less than equal to norm of xn minus x. Clear? By previous property that we already proved that. By equation number 1, this approaches to 0 as n approaches to infinity. So it implies f of xn minus f of x approaches to 0 as n approaches to infinity, and it implies limit n approaches infinity f of xn, which is equal to f of x. So it implies this f is a continuous function, right? So it means every norm is a continuous function. So remember that every norm is a continuous function. Clear?